every single pointer is going to have this value. Okay? So when I do star P, that's going to be what it points to. Right? If its value is 90, then what star P is what is in that address. So that should be C8. I think when I asked this question, I meant to say that the address of P is that. Because if the address of P is that, then P's value is this, and then star P would be here, C0. But the way the question is asked to me, and I'll make sure I clear this up because I know I just looked at the answers. Okay? The answer here should be C8. Good thing is on the exam, I've executed everything. I don't make this stuff up and just figure it's correct. I'll execute it and make sure it's correct. Okay, so that means if I do star star Q, all right, so that means Q's value is 90, star Q is C8, so star star Q is going to be C0, right? The 0xFF makes your life easier. You're just peeling off the last bite, right? And so then R is going to be, go here, 2,8, and then S is going to be go to 2,8, which is here, which is F8, okay? Now P1, okay? So if P is 9,0, then P1 is going to be, these are long, so it's going to be 9,8. You're going to have to add 8 to it. So P's there, so now when I print that out, that's going to be D8. And then similarly, Q1 is going to be this. So if I want to go to Q11, now I need to add 8 more to D8, because D8 is where Q10 is going to be. So Q11 is going to be E0. So we'll find E0. There it is. 8. Okay. So it's just a matter of following the pointers around. And again, I'll double check. I'm gonna double check this one because I think I should have said the address. And if I said the address, everything gets shifted by 1. I view this as an, I don't mean for y'all to get mad at me when I say this. I view this as an easy problem. Like, if I'm giving this to you on an exam, like on the exam on Thursday, how much time am I figuring this one's going to take? 7 minutes? 8? About what I gave you. Okay? It's you know, maybe 10 with a whole bunch of double checking. Right? But this one's not very fancy. It's just straightforward. The only parts that are slightly confusing is here because you have to figure out where do I add what. As I said, I will double check and make sure that the answers that I post are correct. All right. I'm not going to look at the reports because I think the answers on there are wrong. Okay. That was a fun interlude. Back to assembly code. Okay, now we've learned about local variables. The next thing to learn about are parameters. Well, let's start with procedure calls. Okay, so let's go back here. There we go. Okay. So now we have a simple program that has a procedure call in it. No arguments passed to the procedure call, but there is a return value from the procedure call. Okay. So let's go back to our tag war here. Junk.js. Okay. Let's start with A. Yeah, let's start with main. Okay. First instruction should be, you didn't think you were going to be asked a question today, did you? Push 4. You know, we got one local variable, that's 4 bytes. First thing we got to do is put them is allocate room for them. So push 4, and then here, remember I is at FP. Okay. All right. Now we're going to make this procedure call. The way you make a procedure call is you call JSR to the procedure. Okay. And then when you're done, when the procedure's done, if there's a return value, it's going to be sitting in R0, register R0. That's the convention we're using here. So if I want to store that into I need to say store R0 into FP, and I'm done. Okay. Now A, what it's going to do is all it needs to do is to move 1 into R0 and return. Okay. Now, what goes on in the middle here is a lot of junk. All right. And we'll take a look at it and I will describe it. Well, no, I'll describe it first. Okay. JSR does the following things. Okay. 1, it pushes PC plus 4, yes, onto the stack. Now, why PC plus 4? Because if I'm executing this instruction here, the JSRA, this instruction is at PC plus 4, right? When I'm executing this, the program counter is pointing to this address in memory. So the next instruction after when my procedure is done, the next instruction that it should be executing is that one, which is 4 past the PC. So I'm going to do that. Okay. 2, it pushes FP onto the stack. Okay. 3, it sets FP to the current value of of SP. And then 4, it sets PC to A. All of this is done by the hardware. So this isn't something we emulate in software. When this instruction, JSRA, does these 4 things all in one instruction cycle. Okay. So let's look at it. So wish JASM practical. Oh no. There we go. Okay. So, first thing we do, allocate room for I. There's I at the frame pointer. And now JSRA is going to do these 4 things, right? So, what's going to happen? It's going to push PC plus 4 onto the stack. So sitting here at 444 is going to be 1010, right? This hex, that plus 4. Okay. Then it's going to push the frame pointer on the stack, so you're going to see FFF448 onto the stack. Okay, and the SP is now pointing up here to 43C. And then, so the stack pointer will be 43C, and the frame pointer will be set to the stack pointer, so the frame pointer will also be 43C. And then the PC is going to get set to A, which is 0x1000, and now we're going to be running that code. So let's press step and see it all happen. Okay, so PC plus 4, old value of the frame pointer. These guys are now pointing to a fresh stack frame. PC has been changed to 1000, so it's executing A. Okay, and now, so basically what just happened was we saved enough of the stack frame that we can now give this new procedure a new stack frame, and we know how to undo it when we return. So how do we undo it when we return? So we'll move 1 into R0. And now what do we do when we return? Well, we are going to pop the frame pointer off the stack. So the stack pointer will go down 1, and the frame pointer's value will be set to 448. And then we're going to pop the program counter off the stack, so that now the stack pointer is going to be pointing here, and the PC is going to be 1010, and now we're magically executing the next instruction after the JSR call. So, boom. Okay, again. Frame pointer got popped off the stack. program counter got popped off the stack. And now we're running, and lo and behold, we're back in our old stack frame. Our stack frame has been restored. Okay. And now we've got that return value, which we'll put where we want, and we're done. Questions so far? Not every machine works this way. Okay, but this is kind of like the simplest execution model. They all do stuff like this. There's just there could be a lot more stuff you do when you have architecture to do. Okay, let's continue our tag war. All right. Now we got a bunch more junk. And so now what we're doing is we're going to do a procedure call. We're going to learn a couple things. We're going to have a procedure call, and it has parameters with it. Okay? So let's go ahead. Oh, we can keep that. All right, let's do main. First instruction of main. Push 12. Okay. And as always, whenever you do this, and I guess you're not writing assembly code, I always like to say, all right, FP minus 8 is I, FP minus 4 is J, FP is K. Now, I'm going to set I equal to 3, so move 3 into R0, store R0 into I, which is FP minus 8. Going to do the same thing with J and 4. All right, so that'll go into FP minus 4. And now, we got to deal with parameters. The way parameters work, is that you push them onto the stack in reverse order. We'll put that one in little asterisks because it is that important. Okay. Then call JSR. Then call pop to get rid of the parameters. And if there was a return value, it's in R0. Okay? So this is the way you have to set it up. So knowing that, what do I need to do? The first thing I need to do is push I onto the stack. So to do that, I have to load I. So I is in FP minus 8. And put that into R0. And then I'm going to store R0 onto the stack. This is where that little SP minus minus thing comes in handy, right? Because that pushes onto the stack and then it decrements the stack by 4. Okay? Now this other one, what do I have to do? I got to load J, so load FP minus 4 into R0. I'm going to add R0. Tag war, I get to invent something. I have 3 read-only registers in my machine. G0, its value is always 0. G1, its value is always 1. GM1 is always minus 1. That way I don't have to, that way I can do things that involve those values in one step, rather than having to do a move and then work with them. So here, that's going to add 1 to it, put the result back into R0. Now I'm going to store it onto the stack, R0 onto SP minus minus. Now I make my JSR call, JSRA. Then when I'm done, I'm going to pop what I pushed onto the stack, so pop 8. And now my return value is sitting there in R0, so I can set that to K. So store R0 to K, which is at FP. All right, and then I'll move 0, 0 into R0 and return. Okay, now A. First thing A does, push 4. Because now we have K is FP. Let's also think about our arguments. All right, so we push the arguments onto the stack in reverse order, okay? When we call JSR, what happened? PC gets pushed on the stack, FP gets pushed on the stack. So when I'm running here in A, 4 bytes below the frame pointer is the old frame pointer. 8 bytes below the frame pointer is the old program counter. 12 bytes below the frame pointer is the first parameter. 16 bytes below the frame pointer is the second parameter. That's how you do it. That's why we push them in reverse order. Because when we push them in reverse order, the first parameter is always at FP plus 12. And the second parameter is always at FP plus 16. And this is why if you don't put enough parameters to your procedure call and you think you're using too much, you get to be in a world of hurt. Because you're going to be looking at FP plus 20 or FP plus 24, and if you didn't put something there, you're going to be in trouble. Okay? So, I is FP plus 12. J is FP plus 16. So, okay, so if I want to do I plus plus, what do? I load I, load, FP plus 12 into R0, and then add R0, G1, put the result into R0, okay. J minus equals 2, great, load FP plus 16 into R0, move -2 into R1, add R0, R1, put the result into R0. I always like to add rather than subtracting. I don't know about you all, but if I can organize a computation where I'm adding rather than subtracting, my brain feels better. And if you ever learn Galois field arithmetic, addition equals subtraction. It's such a wonderful world where 5 plus 5 equals 0, as God intended.
That add instruction where you put it into R0 and then load into R0, you have to store that first?
I need to store it here. Store R0 into FP plus 16. Is that what you're asking?
Actually, the add instruction before that, right before you load FP plus 16.
Oh, I need to store it. Thank you, Team Plank. Yeah, absolutely right. Sorry. Thank you. Okay, so. Yes?
Would the offsets to the frame pointer look any differently if we were using, say, short instead of?
Oh, that's a good question, and the answer to that is that my machine architecture does not do anything but 4-byte integers. So I avoid that issue altogether. In reality, what happens? Your shorts and your ints, your shorts and your chars are going to get pushed into 4-byte quantities anyway. The only one, now the doubles won't. The doubles will go into 8 bytes, and that's why sometimes you may have had, I don't know if you've ever seen where you have printf errors. If a printf doesn't check you, sometimes printf thinks it should be getting 4 bytes and you give it 8, or it thinks it should be getting 8 and you give it 4, and then your printf looks off. That's what's going on, is it thinks it is. But the shorts and the chars, they'll all get padded. They'll all get padded to 4 bytes. Yeah. All right, and that's J minus equals 2. Here we got this one, so K equals I times J, so we can't remember anything, so we got to load I into R0. Let's load J into R1. We'll multiply them, multiply mul. R0, R1, put the result back into R0, store it back into K, store R0 into FP plus 20, because that's where we're going to, no, to FP. That's why I always put it up here, so I can remember. And now I've got to put FP, I'm going to return 0. No, I'm returning K. God, I'm confused. So I got to load K, FP, into R0, and return. Okay. Let's run it. No! Do I have something wrong? Oh, thank you. Team Plank. Yep.
What do you mean, like
if you care about memory,
Okay.
your shorts will be stored in 2 bytes in memory.
Okay.
Typically, when they get used, then they get unpacked into a 4-byte or 8-byte quantity anyway.
Okay, so it's like.
Yeah.
Okay, gotcha.
Okay. Now, these days, nowadays, with machine learning, there are certain machine learning models which train effectively on like 2-byte floats and stuff like that, and so your GPU may well even have instructions that do it. So there are those things will happen, but in normal standard operation, your short's getting unpacked, your char's getting unpacked, right? But when you're representing a whole bunch of chars, you're only going to represent them in a single byte, and that saves space.
Okay, gotcha.
Okay, we'll run JASM on it. Oh, dang it. Why didn't you tell me? And Mr. Squires tried. I was just about to crow that I hadn't had a syntactical error yet. Oh, no. What?
There's another one, like 5 lines above.
Copy paste error? Yep. There we go. Nothing's too exciting, except for when we get to the JSR call. So, will this work? Woohoo! Look at that user interface. All right. Allocate room. We got IJK, right? IJK sitting there. So now we're going to set one of them. I forget which one that sets. It gets IJK. So that's setting I. That's setting J. Okay. Now what we're going to do is we're going to put I onto the stack. So, boom, I is on the stack. Because I need to make my procedure call. So there, I put I on the stack. Now I'm going to put J plus 1 on the stack. So I've got to calculate J plus 1. So load, calculate J plus 1. That's in there as 5. I'm going to store that 5 onto the stack. Boom. Okay. And you see, this is why I have to reference things from the frame pointer. Because the stack pointer is changing. So I need to reference my variables from the frame pointer. And now I make my JSR call. Okay. So I make my JSR call. Now, got the new program counter, which will be this one, or that should be what's stored. Yep, there's PC plus 4, stored. Old frame pointer and stack pointer are pointing to the stretch stack frame. This is pointing to A. And now all this is kind of boring. Well, it's going to load, it wants to get its first argument, I. It needs to do that by going 12 down from the frame pointer to get that 5. All right. So there's the 5. I'm going to add 1 to it, make it 6, store it back there. There it is. Right? Same with the J minus equals 2. So let's get the J, put negative 2 into that, add them up, store it. Right? So there, now J has 2 subtracted. And so you should also see, right, this is how call by value works. Right? Because when I make my procedure call parameters, I have new memory allocated for that parameter. So when you change that parameter and then you return, it all goes away. It's all sitting on the stack above you. Okay, this one's going to do the multiplication. So multiplication. We've done that. I guess it's 6. Store it into K. K should be here. Yep, there's the 6. Then I load it, 6 back into R0, return, boom. Right? Now we're back. Right? So we're back. First thing we got to do is call pop8 to get those 2 arguments off the stack. That's right there. Okay. Then I store the return value, which is sitting in R0. Okay, and I'm done. All right. Takeaways from this. This is actually a good stopping point. This is all in the lecture notes. If you care, I know you're not getting tested on it, or something you're not getting tested on. I'm not really sure about that. You wouldn't care until May anyway. Got a lot of pictures, which do the same thing as the JASM, but not bad to go through these points. A lot of things in the lecture, okay? JSR does 4 things. Program counter plus 4, frame pointer, set the frame pointer to the stack pointer, set the PC, okay? The return statement undoes it. So what does it do? Actually, I forgot to mention this. The first thing it does is it sets the stack pointer to the frame pointer. Okay? So you don't have to pop your arguments. You can call push 8 to allocate 8 variables, but when you call return, the first thing it does is set the stack pointer to the frame pointer. Then it's going to pop the old frame pointer off the stack. It's going to pop PC plus 4 off the stack, and now you're running that at the location right after the JSR call. Okay? When your procedure has arguments, you got to push them on the stack in reverse order. Okay? Thus, when the procedure is called, the first argument is sitting there in FP plus 12, the next one's FP plus 16, et cetera, et cetera. You know, and I'm probably not testing you on this, so it's okay, right? Because I know, like, have you all learned assembly code before? And where there are like weird argument pointers and registers that store arguments and all sorts of other shit, right? I know it doesn't match here. This is simpler. Okay, but fortunately, I'm not testing you on it, so you don't have to hold 2 things in cache. But that's how these things work. Okay, when procedure returns its value, it's returned in R0. Okay, if you've pushed arguments, got to pop them. First thing you do after your JSR call is pop the arguments. Okay. All right. What this long sentence here says is that although you don't ever read variables above your stack, they have values and they're deterministic by knowing what the machine architecture does, right? When I was done with that procedure last time when I was back in Maine, the stack's containing some stuff, right? And that stuff's deterministic. It's just unused. Okay. Blah, blah, blah. We're all good. All right. I'm not going to be here on Thursday, so good luck. Study up, eat your Wheaties, get ready for it. Okay.